Hello, we are the Group 23. Today we will present our project. Our work is based on the paper How Balls Roll Off Tables by Michael Bacon. It was published in the American Journal of Physics in 2005. So, in introductory physics, a ball rolling off the table is usually treated as a simple projectile. The assumption is that the ball reaches the edge with horizontal velocity v0. It immediately loses contact with the table and then moves only under gravity. And using this model, the landing distance is given by the following formula. However, Michael Bacon, asked the question, does the ball really leave the table instantly? And in reality, the center of mass can move beyond the edge while the ball still remains in contact with the corner. And during this short period, the table exerts a normal force and a friction force on the ball. And these forces can modify both translational and rotational motion. As a result, the ball may land farther than predicted by the simple projectile model, and this phenomenon is known as the kick effect. So, studying this motion, Michael Bacon introduced three main motion stages: rolling before the edge, no slip motion around the edge, and the short slipping free body phase. And only after these phases, the ball becomes a projectile. To understand how a ball leaves the edge of the table, Bacon first analyzed the motion assuming pure rolling without slipping, the no slipping phase. At every instant, three forces act on the ball. The first force is gravity. It always points downwards. And the second force is the normal force from the table edge. The third force is static friction, which prevents the ball from sliding. We describe the motion of the ball by the angle theta, measured from the top of the table edge. And because the center of mass moves along a circular path of radius r, the ball experiences centripetal acceleration. So, given those conditions, applying Newton's second law in the radial direction gives this equation. It tells us how the normal force changes as the ball rolls. Next, applying Newton's second law in the tangential direction gives this equation, which determines the friction force required to maintain rolling motion. Then, since the ball is a solid sphere, its moment inertia is given by this torque equation. And using the torque equation and the rolling condition, Bacon combines the translational and rotational equations, and after simplification, he obtains this equation, and this one completely describes the rolling motion while slipping is absent. At first, it may seem that the ball can continue rolling without slipping all the way until it loses contact with the table. However, Bacon showed that this is impossible. The reason is that the static friction is limited. The maximum available static friction is given by this condition. As the ball moves farther around the edge, the normal force decreases. At the same time, the amount of friction required to maintain pure rolling increases. And eventually, this ratio reaches the coefficient of static friction. At this instant, the surface can no longer provide enough friction, and the rolling constraint breaks down. The ball begins to slide while still rotating, and this means that pure rolling motion ends before the ball actually leaves the table. This one was actually one of the key discoveries of Bacon's paper. Then, after static friction fails, the motion enters the second stage called the sleeping phase. Now, the friction force is no longer determined by the rolling conditions. Instead, it's given by kinetic friction. Because the ball is both rotating and sliding at the moment, the equation becomes more complicated, and Bacon derives it as given on the slide there. This equation predicts the angular position and velocity of the ball during slipping. The normal force continues to decrease as the ball moves around the edge, and eventually the normal force becomes zero. At this moment, there is no contact between the ball and the table. The ball separates from the edge and begins ordinary projectile motion. In other words, that's the point when ball leaves the table. And the important point of this phase is that the launch velocity is not exactly the same as predicted by a simple projectile model. The slipping phase slightly changes the final launch conditions, and this is what produces the kick effect. The simulation of this motion will be now presented by my teammate Jean-Nour.
Okay, let me demonstrate our simulation. As you can see here, we have two possible paths. Yeah, first one illustrates simple projectile motion, while the second one illustrates full motion, which includes a short period of like no slip phase and projectile motion. Here we can, on the right side of our web, we can regulate the radius of the ball. And as we can see here, actually the difference between simple motion, simple projectile motion, and full motion is proportional to the radius of the ball. And at the same time, if we'll increase the initial angular velocity, the difference decreases. Also, we add some values like Table's height, gravitational force, simulation speed, and kinetic friction coefficient. Here we also have other graphs that illustrates variables like theta or alpha that we can see here, and we calculated it using the formulas provided in the paper. And here we have normal force, and the interesting thing is that if we look at this part when the normal force decrease sharply, it happens when the ball rolls off, like it stacks, like rotates at the edge of the table. And also here we have landing distance graph that illustrates simple projectile motion and full motion. And as we can see here we have omega I and landing distance. For small omega I, full motion and projectile motion has quite significant difference. However, when omega I becomes larger, the difference becomes smaller. Yeah, and that's all. Here we have some notes about formulas and possible error sources.
So, to test the ideas presented in Bacon's paper, we performed a simple experiment using a lightweight plastic ball. The ball had a mass of 2.8 grams and the radius of 2 centimeters, and it was released from the rest at the top of a ramp with a vertical drop of 10 centimeters. After rolling down the ramp, the ball traveled across the table and left the edge of a table that was 80 centimeters above the floor. The horizontal landing distance was measured from the edge of the table to the point where the ball first touched the ground. And this experiment was repeated 5 times under the same conditions. Before analyzing experimental data, we calculated the theoretical landing distance using just projectile motion. The launch velocity of the ball was determined using conservation of energy, and for a solid sphere, this equation for inertia was used. And because the ball rolls without slipping, this formula was used. And substituting these expressions and simplifying gives this value for velocity. Next, the time required for the ball to fall from the table height of 0.8 meters was calculated as follows and gave 0.4 seconds. Hence, the distance resulted in 19.9 centimeters. So, now we can compare the landing distances that was observed experimentally with theoretical value. The average experimental distance was 24.4 centimeters and the theoretical distance is 19.9 centimeters as was told before. So the experimental result exceeded the theoretical prediction by approximately 4.5 centimeters, corresponding to a difference of about 22.61%. So the experimental landing distance was larger than the value predicted by classical projectile motion. Therefore, the experiment is consistent with Bacon's conclusion that the motion near the edge of the table is more complex than the simple projectile model suggests, and that the actual landing distance might be larger than it can be predicted by only projectile motion. The results indicate that rotational effects and the interaction between the ball and the table edge may slightly modify the launch conditions, producing a small increase in horizontal displacement, and therefore the experiment provides qualitative support for the main ideas presented in Bacon's paper. This is the end of our presentation. Thank you for your attention.